Why was the discovery and synthesis of quantum dots awarded the 2023 Chemistry Nobel Prize? To answer this question, in this video I'll explain what quantum dots are, how they work, and what each prize winner contributed to their discovery and synthesis. I will finish by explaining their current and future uses. Quantum dots are essentially tiny crystals, typically made of materials like cadmium selenide or cadmium telluride, on the nanometer scale that, at their smallest, typically have diameters between 2 and 5 nanometers, equivalent to tens of atoms. They are so small, in fact, that quantum effects, like quantum confinement of their electrons, occur. Quantum confinement, which is how, due to quantum mechanics, as the size of material decreases, the band gap increases, where the band gap is pretty much the energy that an electron in the valence band needs to gain to move into the conduction band. This means that electrons in smaller quantum dots need to gain more energy to move up into the conduction band, which means that they emit higher energy photons when they move back down into the valence band. This means that shorter wavelength and higher frequency photons are emitted if the quantum dots are smaller, which equates to a blue shift in the light emitted as the size of quantum dots decreases. This means that larger quantum dots mostly emit light on the red side of the spectrum, while smaller quantum dots emit light on the blue side of the spectrum. Now let's get into the details of the three scientists who contributed to quantum dots discovery and synthesis, in the order in which they made their contribution. Alexei Yefimov, a Russian physicist, performed a series of experiments in the 1980s involving making colored glass tinted with copper chloride at a range of temperatures between 500 and 700 degrees Celsius and a range of heating times. He then observed that different sized copper chloride crystals formed depending on the temperature used, and the color of the glass depended on the size of the crystals. Yefimov published his findings in 1981, and in essence he discovered quantum dots. In 1983, Louis Bruce, an American chemist, discovered that if he left particles of cadmium sulfide in solution so that their particles grew, the optical properties of the solution changed. He came to the same conclusion as Alexei Yefimov, although he had not come across Alexei's work, that the particle size in solution led to different quantum effects which altered their optical properties. Both Bruce and Yefimov's contribution was linked to the discovery of quantum dots and their size-dependent quantum effects, while the third laureate's main contribution was developing a method for manufacturing uniform quantum dots, as the methods used by Bruce and Yefimov to produce their quantum dots couldn't make them with a uniform size and shape, limiting their use in applications. Munji Buendi, a researcher at MIT, developed a simple and easy method for synthesizing quantum dots at a uniform shape and size using hot injection technique, where the substances used to make the crystals were injected into a hot solvent to a point where the solvent around the needle is saturated, meaning that nanocrystals formed in that area. He then increased the temperature of the solvent to make larger crystals, to reach a specific size of quantum dots. Due to quantum dots' size-dependent optical properties, they have many potential uses. They are commonly used in electronic devices and electronic screens called QLEDs, which have longer lifetimes, lower cost, and a lower power consumption compared to conventional LED screens. And due to the small size of quantum dots, the devices that use them can be made more flexible, and in some applications, QLED screens can even fold like origami. Their use in medicine is now becoming more prevalent. For example, they can be used as a tag to track tumor tissue or map cells and organs to make surgeries easier and less risky. Their future use is being investigated. For example, chemists are seeing if they would be viable catalysts due to their high surface area to volume ratio and low manufacturing cost, as well as a plethora of other applications, as you can see here. Thank you for listening to my presentation. I thought this was a really interesting topic and subject, and I really enjoyed researching it.